to start a mathematical talk by some philosophy. So it turns out that, of course, I'm not a philosopher, but well, I try to study a little bit. And not long ago, I discovered that Nietzsche, Poincare, and Boltzmann, independently, almost at the same moment, had the same idea. So I want to discuss today the birth of recurrence in dynamics by discussing this beautiful idea from Nietzsche, Poincare, and Boltzmann. So let me begin by Nietzsche, 1844, 1900. So let me quote him in a beautiful text that all philosophers know. I now wish to relate the history of Zarathustra, the fundamental idea of the work, the eternal recurrence, the highest formula of a life affirmation that can ever be attained, was first conceived in the month of August 1881. I made a note of the idea on a sheet of paper with the postscript, 6,000 feet beyond man and time. That day, I happened to be wandering through the woods beside the lake of Silvaplana, and I halted beside a huge pyramidal block of stone. It was then that the thought struck me. And here's the pictured photo of the pyramidal block of stone that all philosophers know. This is where Nietzsche had his idea. And the idea has been formulated in two different ways. First, I will read a paragraph from Zarathustra, and then I will read a proof by Nietzsche himself. So the paragraph is this. Again, this is very famous, not among mathematicians, but this is the preliminary for all philosophers. What if some day or night a demon were to steal after you into your loneliest loneliness and say to you, this life, as you know, live it and have lived it, you will have to live it once more and an innumerable number of times. And there will be nothing new in it. But every pain and every joy and every thought and everything will have to return to you all in the same succession and sequence. Even this spider and this moonlight between the trees, and even this moment and myself, the eternal hourglass of existence is turned over and over again, and you with it, speck of dust. And so this is the way Nietzsche expresses it. And then in a fragment which has not been published in his personal notes, he gives the proof that the world is periodic, and that you have to come back again and again and again to the same situation. And you will see that the proof is very mathematical. The proof, here's the text by Nietzsche. If the world may be thought of as a certain quantity of forces, thus it follows that in the great dice game of existence, it must pass through a finite number of combinations. In infinite time, every possible combination would be sometime reached one time. Even more, it will be reached infinitely many times. So he is proving, well, you can say he's proving that any element in a finite group has finite order. He is proving the Poincare recurrence theorem. This is the very same idea in 1881. So I will not continue in this direction because philosophers have written books and books on this topic, but let's go to mathematics now. But I think it's very interesting to note that this idea of recurrence, Poincare recurrence, etc., appeared in several different heads at the same moment. So let's go to Poincare. Poincare also had the same idea, not in 1881, but 9 years later, in 1990. For him, this sudden idea of recurrence was not in the same kind of pleasure as it was for Nietzsche. As you can see, Nietzsche was struck by this beautiful idea. But the situation for Poincare is very different. He wrote a big memoir on the three-body problem, again, celestial mechanics. This memoir won the prize, 3,000 francs. He was young. 3,000 francs was a lot of money for him. And he won the prize. And when the printer was about to print, or after the printer printed the memoir, Poincare discovered that there was a big mistake in the manuscript. So the memoir of Poincare was just wrong. And under pressure, under high pressure, Poincare had to write it again. He tried to fix it. He could not fix it. And he could not fix it because it was wrong in a fundamental way. And when he fixed it, he replaced a theorem about stability of the solar system by some weaker version, which is Poincare recurrence. So he produced this idea, which has the same proof as Nietzsche. He produced the same idea under pressure, and I probably was not very happy with that. So here's what he writes in the introduction of his new version of the manuscript. He writes that the following paper tries to prove stability of the solar system, blah, blah, blah. It's a new version of a previous memoir that I presented, blah, blah, blah. And in a hurry, I had to state some results without proof. So yeah, he's always like that. He's proving theorems with no proof. And so he had to rewrite the paper again. And then he says the following: I was not able to solve rigorously and completely the problem of the solar system, taking this phrase in a strict mathematical sense. The use of integral invariance did, however, permit me to attain some partial results, which apply especially to the so-called restricted problem where the two principal bodies travel in circular orbits while the disturbed body has negligible mass. In this case, one leaves aside some certain exceptional trajectories whose realization is infinitely unlikely. One may show that the system will return infinitely often as close as one likes to its initial position. This is the case that I have called Poisson stability. You see, this is the same statement as Nietzsche. So here's the mathematical theorem that the way Poincare expresses it. Well, suppose a point is moving in a domain with finite volume, and you look at any small region in it, and then there are trajectories where we cross this region infinitely many times. The proof that Poincare gives is remarkable. Note that in 1890, there was no Lebesgue measure. There was no measure theory. But if you read the paper of Poincare, you can guess that he understood measure theory. He is dealing with measures in the right way, taking countable intersections and not making any mistake about measures. So the theorem of Poincare, you know it. It says the following. You take a probability space, X, with a probability measure mu, and you get a transformation T that goes from X to X, and which preserves the measure mu. Then the theorem there says that for every measurable set A with positive measure, almost every point X in A comes back an infinite number of times in A. In other words, more mathematically, what?
Finite total mass.
Finite what?
Total mass.
Probability.
Finite definition.
You know what probability is? The probability is a space with total mass 1. Okay. So in other words, for almost every point A, x in A, there exists an infinite number of times nk, such that t to the nk of x comes back to A. So this, as all good theorems, has a very simple proof. I guess you all know the proof. You take this domain A, you take its image t of A, t of t of A, t of t of t of A, and you get an infinite sequence of measurable sets, all with the same probability measure. And since the total mass is 1, these sets cannot be disjoint, so there must have been some intersection between two of them. And as soon as you have one intersection between two of them, that means you have found one point which is coming back to the original A. And you just play a little game, not difficult to show that as soon as you have one point, yes?
What's the definition of reserved measurement?
Poincare is only dealing with homeomorphisms. So 1-to-1. I see what you mean. The inverse of T. So he is only dealing with actually with analytic maps. So he's dealing with celestial mechanics. Okay. So that's the theorem of Poincare. Now, let me give you an example and a counterexample. You have this famous Arnold cat map. It's a map from the torus to itself. xy goes to y, x plus y. And it's area preserving because the determinant, the Jacobian determinant is -1. And you take a small cat, take its image, poor cat, and then you take the image, and you take the image, and you take the image, etc., and the cat doesn't seem to come back. It looks like counterexample. However, some 30 years ago, some journalists, I love journalists, not joking, I mean, they have a hard, my son is journalist. So they had the idea of, as an illustration of the theorem of Poincare recurrence, to take a picture of Poincare and to take the transformation under the cat map and to show that Poincare comes back. So let's have a look. I have a small movie. Okay, so first iterate, second iterate, third iterate, fourth, 5. Poor Poincare. And after 240 iterates, he's back. So the journalists claim that this was an illustration of Poincare recurrence. So I want to convince you that this is not at all an illustration. And I will show you that you can play similar games with different results. So I'm going to show you now a picture that looks like Poincare. This is the same picture. I'm not cheating. Huh? This is the same picture. And I will iterate it again 240 times. It's not exactly the same picture, but you cannot distinguish between the two pictures. So here it is. OK, it looks like Poincare. I iterate a certain number of times. I wait. I'm not cheating. This is the computer. I'm not doing anything. The computer is computing. OK. And after 240 times, oh no. So. So how did I produce this? How did I produce this movie? Very easy. You take the picture of Marcelo, and you iterate negatively. Let's say 240 times. So after 240 times, Marcelo has been completely mixed. So the picture of Marcelo after 200 negative iterates is just a gray picture. No structure, nothing. You superpose this picture to Poincare. So what you will see is Poincare with a background of Marcelo, but Marcelo completely unstructured. And then you iterate, and this is the picture that you have seen. You have seen the picture of Poincare superposed with the blurred Marcelo. And then you iterate 240 times, or 200 times positively. Then after 200 iterates, Marcelo is back. But Poincare has been destroyed. That this is what you have seen. Okay? So you cannot say, so let me say it as a summary. Poincare recurrence theorem says that points come back, but not pictures. Don't forget that, yeah? Yes. Okay. So I discuss that now quickly. Suppose you have on your screen a finite number of pixels, like m pixels, like 1 million pixels. And suppose you take a permutation, since we have discussed an each idea, take a permutation of 1,000 points. And you ask yourself, what is the average, what is the expected order of recurrence of a random permutation of a big set with m pixels? Here's a theorem. The average value of the logarithm of the order of a permutation with m elements is equivalent to 1/2 of log m squared. So take m is 1 million. Log m is 6. Log m squared is 36. 1/2 of log n squared is 18. So you should expect an order of recurrence of 10 to the 18. So if you take a picture with 1 million pixels and you permute the pixels, the expected number of times you have to iterate is not 240. It's 10 to the 18, which is a huge number, which is much bigger than everything else you can think of. So already this 240 of the journalists is suspicious. You should not have such a quick recurrence for the picture of Poincare, even after discretization. Now, it turns out that the cat map is not any map. It turns out to be a linear map, even better with integral coefficients. So here's a theorem, a little theorem that I proved a long time ago, which is just for fun. It's an exercise in very elementary number theory. You take an element of SL2 of Z mod NZ. For example, n is 1,000. If you discretize your screen 1,000 on 1,000, you replace your screen by Z mod 1,000 squared, and you iterate the matrix. And the theorem says that the order of any element on this finite group, SL2 Z mod NZ, is small, at most 3n. So when n is 1,000, this theorem says that if you iterate the picture 1,000, 1,000, you should expect a recurrence time of the order of 3,000. 3,000 is more reasonable than 10 to the 18, but still it is much bigger than 240. And the other theorem is that if you are clever or if you are not honest, like this journalist, if you choose the resolution of the screen in such a way that the recurrence is quick, then you can make it much better. And the theorem is this. There exists an explicit sequence of numbers It's like a Fibonacci sequence growing very fast, phi k, which is such that if you discretize your screen by this number of pixels, then there is the return time for phi k is 2k, which is very, very, very small as compared with k. So, for example, if you take phi 17, you have 3,571, which means that if you are clever enough to choose the resolution of your screen to be 3,571, and if you put the picture of Poincare on this resolution, Poincare will come back after 34 iterates. Very quick, okay? But if you discretize your screen by 3,570, with one different pixel, you should expect a recurrence time much bigger than that. So once again, pictures don't come back. If you believe journalists, you should not believe journalists. They have chosen, with my computation, I could compute the resolution of their screen. Okay? Okay. So the moral of my story is, once again, points come back, pictures don't come back. Okay. I recommend a beautiful paper by Pierre-Antoine Guilleneuf, who spent a year here in Rio, in IMPA. He studied that in this paper, what's happening when you take a diffeomorphism or homeomorphism, let's say of a square or a compact manifold or whatever. You discretize the manifold by such finite number of points, and you ask yourself, how long should I wait for the point to come back? This is a wonderful paper asking many questions and proving many theorems, depending on the genericity, C1, C0. Have a look at this paper. It's a beautiful paper. OK. Now let me switch to Boltzmann. Boltzmann is a hero of many physicists, and even some mathematicians. This morning I received a message from a journalist from Le Monde. He asked me, is Witten the only physicist who received the Fields Medal? I answered, he is a mathematician. So the distinction between Boltzmann and the physicist and mathematician is unclear. Okay, so here's the picture of Boltzmann. And Boltzmann, in 1884, formulated the so-called Ergodic Hypothesis. And let me read what he writes in 1884. The great irregularity of the term, of course he writes in German, huh? The great irregularity of the thermal motion and the multiplicity of forces that act on the body from outside make it probable that the atoms themselves, by virtue of the motion that we call heat, pass through all possible positions and velocities consistent with the equations of kinetic energy, and that we can therefore apply the equations previously developed to the coordinates and velocities of the atoms of warm bodies. So he says that if you take a gas in a big box, it's moving in a very complicated way. Of course, you have the preservation of total energy in the box. The kinetic energy is preserved, as he says. And what he says is that the motion of the gas is so complicated that it goes through every point with the given energy. Well, many historians and physicists have discussed that a lot. Is that possible, that a dynamical system might go through every point? Well, physicists, some historians claim that Boltzmann is making a mistake. Some others say that Boltzmann in mind was finite. He was convinced that the world is a finite set. And then he was using the argument of of Nietzsche. But it turns out that a few years later, in 1892, you can see a reformulation of the ergodic hypothesis of Boltzmann. He does not claim anymore that the gas is going through every position. He says almost every position. He says, look, all possible sets of values of x, y, and theta, which are consistent with the equation of vis viva is kinetic energy, are obtained with any required degree of approximation. I will not read the German, provided the motion continues for a sufficiently long time. So this is a modification of the ergodic hypothesis. Initially, he said the trajectories passes through all points in the configuration space, in the all points with the given energy, but now he moves it a little bit, and he says it passes arbitrarily close to any point. In other words, trajectories are dense. Instead of saying that trajectories are full, now trajectories are dense. One comment. The Peano curve, filling a square or filling a box, has been invented by Peano in 1890. So you have to know that at the time, this concept of dimension, of what is a curve, what is a smooth curve, what is a continuous curve, everything was complicated. So you should forgive Boltzmann when he says that the trajectory passes everywhere. And actually, you have to wait until 1913, when two famous mathematicians wrote a paper, actually wrote two papers, in Annalen der Physik, proving the following theorem. A flow on a manifold of dimension bigger than 1 cannot have only one orbit. It is not possible to have a flow which passes through all points of the manifold. Well, it looks obvious for you. Please prove it. I'm sure that the proof is tricky. Patrice, you can prove it? How do you prove it? You know, Bear was a young man at the time. Okay, so this is I mentioned that to show you that all these things seem easy to us because yeah, you know Bear theorem. You have been knowing Bear theorem for 40 years, no? It's completely natural to you. It was not the case at that time. Okay, so let's go to von Neumann and Birkhoff. Well. Von Neumann was born in 1903. This is why I chose the portrait where he looks young. And Birkhoff in 1884. So you can see that these two mathematicians were not of the same generation. In 1931, von Neumann was a young man, and Birkhoff was a powerful man. He was editor of the Proceedings of the National Academy of Sciences, and one day a student came to his office. The student's name was von Neumann, and von Neumann proposed the theorem, the Ergodic Theorem. As I will discuss that in a moment, the version of the Ergodic Theorem by von Neumann was the L2 version, which was a great theorem, but obviously not the best possible theorem. Immediately, Birkhoff understood that the real theorem might be true with the strongest version, the L1 theorem. And the story is very sad because Birkhoff managed to accept the paper of von Neumann, but after his own version of his own theorem was published. And you can see how, let me show you. This is the paper of Birkhoff, published in the Proceedings of the National Academy of Sciences, communicated December 1st, 1931, and published in the issue number 17 of this journal, 1931. And what?
He was the editor.
He was the editor, yeah. And he managed to accept the paper for Neumann, for the weaker version, after that, in such a way that the paper for Neumann will be published in 32. So the paper was, according to this publication, communicated 9 days later, but it was published 1 year later in 1932. So this is a terrible behavior from Birkhoff. Well, as far as I know, von Neumann later on was also not all completely honest with students, but that's another story. Anyway, so it's a good example where you have two papers, one proving a strong theorem, one proving the weak theorem. The weak theorem has been proved earlier, but published later. So I want to explain the ergodic theorems and to say something about the proofs. Well, the theorems are written here. You take a transformation from some probability space X with a probability measure mu. You assume that T preserves the measure, and you take a measurable function f. The weak version, the L2 version by von Neumann, says that if you take the averages, sum from 0 to n-1 of f composed of t to the k, this sequence of averages converges in L2 if f is in L2. And the limit function f tilde is an invariant function. So it's a convergence in the L2 sense. And the version of Birkhoff is stronger for L1 functions. It tells you that the same sequence converges almost everywhere to some function f tilde, which is also invariant if the function f is in L1. If you think a little bit, you have to agree that Birkhoff is right, that the second version is much, much more powerful than the first version. So what is interesting is that the proof by von Neumann is too complicated. Nowadays, we have simple proofs. I will show you one in a moment. And the proof of von Neumann was using representation theory on Hilbert spaces. The decomposition of any unitary representation of Z as a sum of one-dimensional representations. That's very easy today in principle, but it's a bit too complicated. And the proof of von Neumann, of Birkhoff, is very complicated. I had the opportunity to teach 3 times a course on ergodic theory. The first one was here. I was using the book of Magnier. And I remember very well that one day I came to Magnier. I said, Ricardo, there are some mistakes in your book. I took notes of them. Maybe you would be interested by a list of those mistakes for the next edition. And Ricardo told me, keep your paper, I don't mind. So he was not interested at all by fixing the mistakes. And I used the proof of Magnier of ergodic theorem, which was very complicated. And much later, there was a proof which was published by Katznelson and Weiss, which is much simpler than the original proof. But it is simpler, no doubt. But still, I keep forgetting it, which is not a good sign for a simple proof. So I want to prove the theorem of von Neumann, and then I want to begin the proof of Birkhoff until I forgot it. So let me begin by von Neumann. So this, you have this transformation T from x to x, preserving the probability mu. You consider this represents the Hilbert space L2 of x. And you want to prove that if you pick some element f in the Hilbert space, then this average 1 over n sum f composed with tk converges to some limit in L2 when n goes to infinity. The first observation, very simple, is that the set of f for which this is true is a vector space. If this is true for some f1 and f2, it's true for the sum of the two. The second observation, which is also easy, is that the set of f's for which this is true is a closed vector space. If you have a sequence of f for which this is true, the limit also holds true. Now, there are two obvious subspaces for which the theorem is obvious. First, you have the subspace, I can denote it by I, invariant functions. Those functions f for which f composed with t is equal to f. Of course, those functions f for which f composed with t is equal to f, this is constant. So this is a constant and this is convergent. So invariant functions are obviously in this space of f for which the theorem is true. And the second subspace for which this is obviously true is the subspace of functions of the form g composed with t minus g. Because if you take a function having this shape, g composed with t minus g, when you take the sum, you have a telescope, and the telescope will converge to 0 because you divide by n. So you have this subspace on which the theorem is obvious, this subspace on which the theorem is obvious, and then I put it here dotted line because this subspace might be non-closed, but you close it, and you have two subspaces for which the theorem is true and obvious. And the next and final step is to remark that these two subspaces give an orthogonal decomposition of L2. Why is it the case? Because if you want to use the Hahn-Banach theorem, an element of the dual of L2, which vanishes on these functions, is given by the inner product by some f, which is orthogonal to all of these g composed with t minus g, and to be orthogonal to g composed with t minus g is precisely to be invariant. So the orthogonal of that is that. End of proof. The proof of Birkhoff is much harder. So, as I told you, I will not prove it today because I'm sure I will fail, but I can begin the proof. And what? Yeah. Look, I'm using words and theorems that are familiar to you, but not in 1930. Hahn-Banach and when is even the concept of Hilbert space was brand new at the time. Yeah? Don't forget that we are using the background of our fathers and grandfathers. Things that are obvious to you are not obvious to your father. Hopefully, okay. Well, this is crystal clear, I think. Now let me try to prove Birkhoff theorem. Well, you take this f, and you want to prove that 1 over n sum of f composed with tk converges almost everywhere to some limit function f tilde x. So let me assume assumption 1 that f is bounded. Ah, somebody's calling me. This is my wife. So assume that f is, let's say, f is positive and bounded by some k. This is a first assumption. Then, for each x, you define f bar of x is the lim sup of 1 over n sum x and f bar of x to be the lim inf of the same thing. The theorem of Birkhoff says that f sup and f lower bar are equal. So I am going to show the following. I'm going to prove that the integral of f is in between the integral of f lower and f upper. If I prove that, I'm done. Because, of course, f lower bar is less than f upper bar. So if I can prove that this inequality holds true, then these two things have to be equal. And being equal everywhere means that f upper bar is everywhere equal to f lower bar. So the only thing I have to prove is this inequality. Now the trick is this. You pick your point x, and you choose an epsilon, and you look at some 1 over n, and k is equal to 0 to n minus 1 of f of t kx. And you know that the lim sup of that is f sup of x, by definition. So there should exist some integer n such that this quantity is more than that minus epsilon. So you call nk, n of x is the smallest integer such that this sum is at least f bar of x minus epsilon. Now you want to estimate longer sums. So let me multiply on both sides. N of x. OK, so I have a good estimate for this sum on an interval of length n of x. But I want to use it not on some interval n of x, but this is x, t and k of x, sorry, t n of x, and I know how to estimate the sum here on this interval from x to t n x. Now I want to go further. So from t n x, I can play the same game, replacing x by t n x x. So I have another n, so I know how to estimate the sum until here. So here I know this, I know how to estimate that here. I know how to estimate here. I know to estimate here, etc. I get a sequence of intervals for which I have this good estimate. But I want to get this estimate not for the specific times, but for all times. So I want to estimate this I would like to get something like that. I would like to get something like that for all n's. But I cannot do that. I can do that only for those n's which correspond to these successive hops. So let me make a second assumption. I suppose that the n of x are bounded by some capital N. So if you make this assumption, that means that you have estimates for these times with bounded hops. Now you want to get from some other n, which might not be one of these points, for example here. Well, that's not important because the sum here will be at most n times k, the maximum value of the function. So if you play that game, you have this estimate, and you integrate on, you divide by n. You integrate here, and then you get, and you let n go to infinity, and you get the integral of f, the nu, is greater than the integral of f bar, the nu, and this goes to 0, and I'm done. So the Ergodic theorem is proved, and there are two funny assumptions, that the function is not L1 but L infinity, and that these jump times n of x are bounded. That's the end of what I remember. But this is not so complicated. What happens is that if the function is not bounded, you truncate it. So you replace your function by a min of f and k. And you have a truncated function for which you apply this argument. And this, if this function n of x is not bounded, you truncate it. And then you do not forget your undergraduate course on measure theory, these limits and integral of what's that, dominated convergence, etc., etc. And you let these two truncations go to infinity, and the theorem goes easy. That's what I remember. Anyway, today we have proofs of the theorem of Birkhoff, which are understandable. But I don't know if I proved that I understood it, but I remember at least the structure of the proof, which is not the case of the proof of Birkhoff, which again is complicated, and I keep forgetting it. Recently, I was discussing with Marcelo. I think Marcelo taught many times this course on ergodic theory, and I asked him, Marcelo, I've given you a piece of chalk. Can you prove the ergodic theorem? And he said, no, I cannot. So this is not good for mathematics if you cannot prove all basic theorems yourselves. So I'm not criticizing Marcelo. Myself, I cannot do it. OK. So let me finish by discussing something else. Let me discuss entropy. Yesterday, I told you that Poincare never taught mathematics at the university. You can see here his course on probability theory. I can explain that at the time, probability theory was not considered as part of mathematics. It was considered as part of theoretical physics or whatever, and it was not mathematics. It took a long time in France in order to recognize that probability is part of mathematics. For example, Jean-Pierre Cahan told me that when he entered CNRS as a probabilist, he was in the theoretical physics department. Anyway, so he wrote this book, or more precisely, the book was written by an ancien élève de l'École Normale Supérieure, Mr. Quiquet, who took notes of the classes of Poincare. And this book is really remarkable. And at some moment, he explains what is entropy. And he gives an example. I think this is due to him. I didn't find it anywhere else before. This is the model of shuffling cards. So you play cards. You may have 52 cards on the table, and you distribute them. And the number of possibilities is huge. It's factorial 52. It's a very, very big number, much bigger than the number of neurons in your head. And you have your cards in your hands, and immediately, we poor human bodies, we have some idea about the quality of the game. I mean, you know something because you count how many colored cards you have. You have a certain number, a small number of quantities that you look at, and from that, you have a good perception of your play. And the picture is that you have a huge set. You have a huge set with many elements, and you project it to a small set, which is understandable by a human being. And when you play the game, you have no idea of where you are, but you know where you are projected. And the definition of entropy, as given as illustrated by Poincare in this book, is that the entropy of the so-called microstate here, by definition, is the log of the cardinality of the inverse image. It tells you the log of the number of possible configurations of the cards with the given feeling about it. So here's the definition. The entropy is the log of the number of microstates that cannot be distinguished microscopically from a given one. And then this is basically the definition of Boltzmann in the case of statistical mechanics for a gas, etc., etc. And in his book, in his books, Boltzmann shows that entropy is increasing in time. This is the famous second principle of thermodynamics. Entropy is increasing. And then began a very complicated story about how is that possible, that entropy is increasing. How is it possible to reconcile that with the recurrence theorem of Poincare? The points have to come back and back again, and the entropy cannot increase everywhere, always, since it's coming back. And there is this famous quote of Boltzmann. Somebody explained to Boltzmann that if you take the air in this room, if all of a sudden you change the velocity of all particles in the atmosphere, change them to the opposite, so that you replace the future by the past, then the air will move backward, since the equations of mechanics are reversible. And the entropy was increasing, now it's decreasing. So the answer of Boltzmann was, according to the tradition, okay, you want to reverse the velocity of every molecule in the room, please do it. Which so I think it's a very good answer. Huh? So how can you reconcile this recurrence of time, of the dynamics, with the fact that entropy is increasing? So I just want to show you, it's almost philosophical, an idea of Boltzmann, which is I like very much, even though it is kind of fanciful. So this is a picture of my factorial 52, proving this is all possible microstates in the world, in the universe. And you can see the trajectory of a particle starting somewhere and moving in the in the phase space, and you want to understand why entropy could be always increasing. Entropy, you remember, is the size of the box on the fiber containing X. And here's the idea, the dream of Boltzmann. I think it's an interesting picture. Is the following. Look at the entropy as a function of time. So you have time. So this is the entropy of the universe as a function of time. Of course, frequently you are in the most massive part of the picture, so you will be in the places where the volume of the fibers is huge, so entropy is big. So your particle, I mean the universe, will almost always will be in the place where the entropy is big. And of course, from time to time, very rarely, it has to pass through these small, tiny places where the box is small. So when this happens, the entropy drops. So you have something like that. And then you have to go back again, and the picture is something like that. Most of the time, you are here, and from time to time, you have a decay until to a low value of entropy, and then you come back again in the place where entropy is big. So now here comes the comment of Boltzmann. In this place, entropy is huge, which means that space or the universe is totally disorganized. This is the place where Marcelo Viana is blurred. It does not exist anymore. It's just nothing. And these places where entropy is low is precisely where the structure exists. So according to the dream of Boltzmann, 1890, in these places, the situation is so gray, nothing happens. There is no human being, no culture, no civilization. This does not exist in practice. Nobody is there to look at it. And there, entropy is going down and then up. And according to Boltzmann, in these two moments in the history of the universe, the civilization would exist and would decide, by definition, that time is going in this direction. And here, the human beings would say that time is going in that direction. So the definition of time, the arrow of time, is chosen by our mind in such a way that the second principle of thermodynamics has to be true. So we choose the clocks in such a way that entropy is increasing. So you have long periods of gray moments where nobody is there to comment on the existence of civilization. And in between these moments, you have moments where entropy is changing fast, and then you choose your clock depending on this entropy. So I'm finished, and in order to finish, I want to, of course, to finish with a quote of Poincare. And you will see that Poincare almost said that. He said the following beautiful sentence. Étrange contradiction. Pour ceux qui croient au temps, l'histoire géologique nous montre que la vie n'est qu'un court épisode entre deux éternités de mort. Et que dans cet épisode même, la conscience, la pensée consciente, n'a duré et ne durera qu'un moment. La pensée n'est qu'un éclair au milieu d'une longue nuit, mais c'est cet éclair qui est tout. Merci beaucoup.